Hello, it's a video on thermodynamic lecture series. If you are interested in the topic, sit relaxed, make yourself comfortable, watch, enjoy, and learn. Hello everyone. In this video, we will learn about the fundamentals of thermodynamics. Fundamentals, I mean here as the various terms used in thermodynamics. So the first term is a system, also called a thermodynamic system. To learn about this, consider a glass of water. Now it has got two things, one is a solid and another one is a liquid. Out of these two, glass and water, we can focus our attention on water alone by drawing an imaginary boundary around it. Now we define a system as a quantity of matter in space upon which our attention is focused. This system has an imaginary boundary. Schematically, we can represent a system like this. So this is space, or it's a region in space. This is distinguished from its surroundings by drawing an imaginary boundary. So what is a surrounding? It is anything external to the system is a surrounding. Three-dimensionally, a system is represented like this. Suppose if I put an electric heater inside the glass of water, after a few minutes the temperature of water increases due to the addition of heat, which is a form of energy. Schematically, we can represent energy can enter the system or energy can leave the system. In our example, energy is added. Suppose if I remove the heater, after a few minutes the water will return to its initial temperature. While doing so, it loses its heat energy to the surroundings. Similarly, add water into this glass. Now mass is added. Mass is added. Schematically, mass can enter the system or mass can leave the system. If you drain the water, it leaves. Now we can define three types of system due to the interaction of mass and energy with the system. So the first one is an open system wherein both mass and energy interacts. The second one is a closed system wherein only energy interacts. There is no mass interaction. Only energy interacts. A third one is an isolated system in which there is no interaction of either energy or mass with the system. That means the system is isolated from its surroundings. So having defined a system, we now focus on the next concept called continuum. In order to explain this continuum, we need to consider macroscopic approach and microscopic approach. In macroscopic approach, we consider a certain quantity of matter in order to study the behavior of it. No molecular activity is considered. But in microscopic approach, a system is composed of number of molecules. So in this sketch, I hope you are able to notice minute dots. So these are all nothing but the molecules present in the system. And the behavior of the system is identified by summing up the activities of each molecule. That means the behavior of each molecule. To explain the concept of continuum, consider a small, and before that, in macroscopic, the behavior of a system is identified by the average value. To explain the concept of continuum, consider a small volume delta V of mass delta M in the system, and using this we can define the property density mass by volume. If a plot of density is made against the volume, we will get like this. So closely look at this graph. When the volume is very small, the slope of the curve, that is the density, changes continuously, and after this point the slope is almost constant. Therefore, we can divide this graph into two regions by drawing a line here. So the region to the left of the line is influenced by molecular activity, whereas the region to the right of the line is not affected by the molecular activity. So schematically, if you reduce the volume considered, molecular effects comes into picture, and beyond a certain volume, matter behaves continuous. That means the molecular activity ceases. In thermodynamics, we assume all the systems are continuous, and this concept is called concept of continuum. So having defined a system and assumption of continuum, we focus our discussion to what is called properties. So properties are the characteristics used to identify the physical condition of the system. Example, pressure, volume, temperature. Properties are classified into two. One is intensive property, which is independent of the mass of the system. Example, pressure, temperature. The other one is extensive properties, which is dependent on the mass of the system. Example, volume, energy. Now these extensive properties per unit mass is called a specific property. Example, specific volume and specific energy. So the next term we are going to define as a state. In thermodynamics, a system exists in a definite state. So what is this definite state? When the system properties have a definite value, then a system is said to have exist in a definite state. And a system is said to have undergone a change of state whenever it is influenced by an operation. So what this operation does, this operation changes at least any one property of the system. And to define the state of a system, we need to measure property, and in order to measure the property, we need equilibrium. So what is meant by equilibrium? There are no driving forces within the system. Since there are no driving forces, a system in equilibrium experiences no change of state. And thermodynamics deals with equilibrium states. And for a thermodynamic system to be in equilibrium, it has to satisfy four. The first one is a chemical equilibrium, wherein the composition, means the chemical composition is same. The second one is a phase equilibrium, wherein mass of two phases, say for example solid and liquid phase, reach equilibrium. The third one is a mechanical equilibrium, wherein the pressure is same, and the last one is thermal equilibrium, where the temperature is same throughout the system. And the state of a simple compressible system is specified by two independent intensive properties. So we need two properties to specify the state of the system. In order to measure those properties, the system must exist in equilibrium. So after equilibrium, which is used to measure the property, which in turn is used to define the state of a system. The next discussion is focused on path, process, and a cycle. So, what is this path? It's a series of state changes, and it is transient in nature. So, this series of state change is not in equilibrium, it is transient. So, what is a process? When a path, that is the series of states, is completely specified, the system is said to have undergone a process. And what is a cycle? It's a series of state changes of a system such that the initial and final states are identical. So these three terms can be represented in graphical form like this. I'm going to plot pressure against volume, and assume there is a system existing at state 1 identified by the properties pressure P1 and volume V1. Due to some operation, assume this system has undergone a change of state and it reaches 2, wherein the property values are P2 and V2. So how the system has gone from 1 to 2? It would have undergone a series of states like this. So these intermediate states are transient. That's why circle with a cross. And if I connect 1 and 2, through the series of states like this, green color line, dotted line, it is called the path. It is called the path. And what is this process? When the path is completely specified, then it's a process. Example, constant pressure process, constant volume process. So constant volume means when the system changes from state 1 to 2, volume remains constant. So the path is clearly specified. That is what the process. Suppose if this system returns from state 2 to state 1 due to some other operation, then the system is said to have undergone a cycle. Observe this graph. So one more operation is bringing the state of the system back to 1 from 2, and if I connect all the intermediate states and 2 and 1, using a dotted line, it's a next process, the next path. So here the system at 1 goes to 2 and returns back to 1. Therefore, the initial and final states are identical, and there is a series of state changes. Now the system is said to have undergone a cycle. In this graph, we represented the intermediate states using a circle with a cross and the path using dotted lines. Why? Because the intermediate states are transient. But in thermodynamics, we assume all succession of states are in equilibrium. So how this equilibrium is achieved? By allowing the change of state to occur infinitely slow. So infinitely slow, and that process is called quasi-static process. So quasi-static means very slow process. Due to this slowness, the deviation from equilibrium during series of state change is less, and hence we are able to achieve equilibrium. So when the intermediate states are equilibrium states, we can use filled circles to represent the change of states, that means the intermediate change of states, and also we can connect 1 and 2 through the various state changes using a continuous line. So quasi-static is hypothetical. So it's an assumption. And now in thermodynamics, there are quantities which are independent of the path followed by the process, and there are some quantities which depends on the path followed by the process. If the quantity is independent of the path, then we give a name to that quantity. So what are the names? As a point and path functions. So what is this point function? Independent. So quantity is independent of the path. It depends only on the points. What are the points? The point is end state 1 and end state 2. So this quantity is independent of the path. It's called a point function. Otherwise, it is a path function. So what is a path followed? Whether it follows a constant pressure process or a constant volume process. So if it depends on the path, then the quantity is called path function. Example for path function are heat, work, entropy. So what are these quantities? Heat, work, entropy, we will discuss in later lectures. Of course, in addition to this quasi-static process, we define two more processes, not two more processes. A process may be reversible or irreversible. To explain this reversible and irreversible processes, consider a system, maybe a compressible gas inside a piston cylinder arrangement existing at pressure P1, volume V1 and temperature T1. So this state is plotted graph 1. In the graph at 1. This is the state 1. Suppose if I compress the system. So compression is an operation due to which the system changes its state. So when I compress, the property values get changed. It goes like this. And the process is represented using a green color line. Remember, we assume quasi-static process, meaning all the intermediate states are equilibrium. Even though the animation is faster, we assume it's a quasi-static process. That's why a continuous line. So pressure increases P2. So earlier the pressure value is here, now it has raised. Volume decreases due to compression. And now if I want to return the system from 2 to 1, what I am going to do, this compressed gas is expanded. That means the piston will move towards right, and when it expands, volume increases, pressure decreases, temperature also decreases. And while doing so, if the system follows the same green color path, if the system follows same green color path, observe the animation of piston movement and also the green color path. So when it expands, this green color line has changed into red color line, meaning the system returns to its original state P1, V1, T1 following the same path. Then we call the process is reversible. Otherwise, it is irreversible. Okay, to summarize what we learned in the topic fundamentals of thermodynamics, we look into the various takeaways. In thermodynamics, we concentrate on certain quantity of matter called a system, which we assume to be continuous. The state of the system is identified by properties which are measured at equilibrium condition. A system may undergo a process through a change of state and may complete a cycle. A process may be reversible or irreversible. Quantity that is independent of the path of the process is called a point function, otherwise a path function. Thank you.